recognizes 3 little tiny pieces of HIV, but a broad T-cell response that can recognize any variant of HIV that you would throw at it. We want to reduce the chance of transmission. We want to use low-risk vectors. I would not use adenovirus. We want to make it low cost, if not entirely free, because the average income in countries like Mali is $30 per year. We want to make sure that this vaccine could actually be made in the developing world. Why should we make the vaccine here? Why can't we transfer that technology to Mali or to Kenya or to Cambodia, where they can actually make the vaccine themselves? And we need to make it with a technology that's scalable, so we can make small research batches and quickly translate to make larger batches in developing world countries. So that's really what we've started out to do. And the other very important point is that this has to be done in collaboration with developing world scientists. If the target is the developing world, you cannot do this in a vacuum. You cannot do this without actively getting scientists in the developing world engaged. So that's what we've been working on. I'll just give you my example, which is the Gaia HIV vaccine, which we hope to be globally relevant and globally accessible. The way that we're approaching this vaccine program is to basically build it based on epitopes. And this is actually a picture of an epitope lying in an MHC molecule. We use computer programs to predict these sequences that are highly conserved in all strains of HIV. So epitopes are the minimum essential unit of information that stimulates an immune response. We use our immunoinformatics tools to identify what we now call these Achilles heels. If the HIV virus is so variable, it still needs to function. There are pieces of the HIV virus that stay the same. Those are the vulnerable targets for HIV. If you can find the sequences that stay the same, no matter which flavor of HIV you're looking at, then you probably have something that will work in a vaccine. So we've focused on these very conserved epitopes. These epitopes that we've selected are not just conserved in one particular year, but we show that they're conserved over time. In the 20 years of the HIV epidemic, as long as we've been sequencing HIV, we know that our epitopes are conserved in all of those viruses. And we also tailor this vaccine so that it can be presented in the immune response of all peoples of the world, no matter what their genetic background is, no matter what their HLA is. And the other concept, as Pat so well summarized, is to make this vaccine a not-for-profit endeavor. So we take computer programs, we basically digest down all of the sequences. Fortunately for us, most of the work has actually been done by the Los Alamos National Laboratory. They have created a huge database of HIV sequences. They're also available in GenBank. We basically dump those into the top of the computer, and what we're selecting, if you want to think about this in a different analogy, if we have all the dialects of French in the world, Haitian Creole, Senegalese French, all the different dialects of French in the world, we're picking out the words. Bonjour, comment ça va, je vais bien, aujourd'hui. The words that are conserved in the French, in the HIV virus, that are conserved in all the different dialects. We use computer programs, and those are the epitopes, the sequences that we're putting into our vaccine. We start with the genome, we predict the T-cell epitopes, we confirm them using blood from HIV-infected patients. We've had donors from all over the world, from Thailand, from Cote d'Ivoire, from West Africa, and also from Providence, donate their blood to have these T-cell epitopes tested. We then clone them into a DNA vector, and we produce also the peptides, and we've been vaccinating. So far just in mice, but we have pretty dramatic results. So this really kind of summarizes the informatics approach. You take all the sequences, you dump them into the top of the computer, you ask the computer to find the letters that are actually conserved, 9 amino acid strings of letters. It's as simple as that. This program is called Conservatrix. It's an algorithm that we wrote to do this. We then find these conserved sequences. This just basically shows how it might look in a sequence. You find this 9 amino acid string, and that's your conserved epitope. We've also developed another program called the epi-assembler, which assembles those conserved sequences into longer ones, so we can get longer sequences that contain highly immunogenic and very highly conserved T cell epitopes to turn on a T cell response. When you look at them over time, this just basically illustrates how well conserved they are. In orange are the epitopes that are conserved not just in a single year, as shown in one of the columns, but across time over the 10, 15 years of the HIV epidemic, that we have selected epitopes that this virus cannot change because it uses that piece of its protein to do something critical. So we found the Achilles heel of the HIV virus, and that's what we're putting into our vaccine. Basically, where we are in terms of the epitopes, we mapped 400 epitopes, we confirmed 200 of them, and that's pretty good when you look at computer programs. We're now aligning them so that when you put the two of these words together, you don't create a new word at the junction. This is a computer program called Vaccine CAD, or Vaccine Computer Assisted Design, that allows you to put epitopes in a string and not create gobbledygook. And then we clone these strings of words into a DNA vector, and that's shown in this picture. We basically take the amino acid sequence, we create the DNA, we then make a vaccine using that DNA. That's our delivery vehicle. We also use proteins to boost the immune response. This is a prime boost vaccine that we're working on, and we test them in mice that have human-like immune systems. That's how we test our vaccine. And I can't show you results from challenge in mice because basically HIV doesn't infect mice. So the best proxy I have are two proxies. One is a vaccine that we've made that's a DNA-based vaccine using epitopes alone, and showing here that we can protect against a very virulent bacterial infection with a vaccine composed just of 14 epitopes. This particular example is tularemia, a biodefense project that we now have funding on thanks to the Bush administration to protect against bioterror. But it's a great model for our HIV vaccine, and we will be doing studies in mice that have a chimeric virus that is created to look like HIV that does infect mice, and we will show that we can protect against HIV infection using this chimeric virus in the mouse model. So that's basically where we are. It's also important to point out that we're working in collaboration with Usman Koita of the University of Bamako, and a wonderful collaborator who has his PhD from Tulane here and is very interested in vaccine, is building a vaccine research building in Bamako so that when we have our vaccine, we can actually test it there. In the meantime, we're working in West Africa, so I have roped some Brown students into doing some basic research with me in the neighborhood where we hope to test our vaccine, and they've been doing what are called CAP studies, knowledge, attitudes, practices, looking at HIV risk behaviors and asking people what they think about getting an HIV vaccine. Would they be willing to participate in a trial? We've done this in a particular region of Bamako, which is the poorest neighborhood in the poorest, one of the poorest cities in the world. The neighborhood is called Sikoro, and over the course of many trips to Sikoro, I finally met the chief. The chief said, look, you know, I know this is a lot to ask. Could you please build me an HIV clinic in my neighborhood? And I said, well, you know, if you never ask, you never get. So let me ask. And I went home and I asked my board, and basically that's what we've been doing. This is a picture of the new HIV clinic that we've built in the neighborhood of Sikoro over the past 3 years. It took us about 2 years to raise the money and about 6 months to build the clinic. But basically what this clinic will be doing is providing state-of-the-art HIV care, accessible